Ever wondered how statisticians untangle the chaos of massive datasets? Imagine trying to predict house prices using 100 variables, square footage, location, even the number of windows. How do you separate the signal from the noise? That's where tools like the Dirichlet-Laplace prior come in. Think of it as a digital filter that shrinks irrelevant variables to zero, letting you focus on the real drivers of the outcome. But here's the twist. Even the most sophisticated tools can have hidden flaws. A groundbreaking study recently uncovered a critical issue with how one of these tools, Markov chain Monte Carlo, MCMC, algorithms, was being used. MCMC is a workhorse in Bayesian statistics, simulating complex probability distributions by sampling from them. The problem? The algorithm was updating variables in the wrong order, like baking a cake by adding flour after the frosting. The result? Flawed results that could mislead entire fields of research. Let's dive deeper. The Dirichlet-Laplace prior works by combining two key components: a scale parameter that controls how aggressively variables are shrunk, and a spike that zeroes out unimportant ones. The MCMC algorithm was supposed to sample from the posterior distribution, the updated probabilities after analyzing the data. But the original implementation had a critical flaw. It updated variables in a way that violated the mathematical structure of the model, like solving a puzzle by randomly swapping pieces. The fix? Researchers found two elegant solutions. First, they restructured the algorithm steps to align with the natural flow of the math, like following a recipe instead of improvising. Second, they rephrased the prior itself, creating an equivalent formulation that's easier to sample from. It's like solving a maze by taking a different path that still leads to the same exit. To validate their solutions, they used a classic statistical tool, the QQ plot. Imagine plotting two sets of data against each other. Perfect alignment means everything's working. The original algorithm's results: a chaotic scatter. The corrected versions: a clean straight line proving the fix worked. Why does this matter? MCMC methods underpin everything from machine learning to economics. A single flaw in the algorithm could ripple through years of research. This study isn't just about fixing a bug, it's about reinforcing the foundations of modern statistics. But here's where it gets even more interesting. Another study compared two Bayesian samplers, the marginal-conditional sampler and the successive-conditional sampler. Think of them as two different dance moves that ultimately follow the same rhythm. The research showed that certain transformations in the successive-conditional method align with the marginal-conditional approach, revealing deeper mathematical connections. The results? When the signal in the data was weak, like faint whispers in a noisy room, the corrected and alternative samplers outperformed the original, cutting prediction errors by half. But when the signal was strong or the data was ultra-high-dimensional, the original method held its own. The alternative approach, however, excelled when parameters were tiny, suggesting it's more robust in edge cases. So what's the takeaway? Even the most advanced tools require meticulous tuning. A single step reordered, a prior rephrased. These small changes can transform flawed algorithms into reliable ones. And as data grows more complex, ensuring our statistical tools are rock solid isn't just important, it's essential.